Now we take second theorem, theorem number 2. Theorem number 2. Theorem number 2. A non-decreasing sequence which is not bounded above. A non-decreasing sequence, sequence which is not bounded above, which is not bounded above, diverges to infinity, diverges to infinity. This is our second theorem. Proof of this theorem. Proof. Non-decreasing sequence which is not bounded above. Suppose sequence Sn. Suppose sequence S suffix n is equal to 1 to infinity is non-decreasing and is not bounded above. This sequence Sn is not bounded above. Therefore, by definition, for given capital M greater than 0, therefore, for given capital M greater than 0, we must find positive integer capital N, or capital N belongs to I, such that Sn is greater than capital M for all small n greater than or equal to capital N. Capital M, since capital M is not upper bound for the set, upper bound for this set, range set, for the set or range set S1, S2, S3 and so on, Sn plus 1, S suffix capital N plus 1 and so on, S suffix small n plus 1 and so on. Capital M is not an upper bound for this set. Therefore, there must exist. Therefore, there must exist positive integer n belongs to I, such that Sn is, S suffix capital N is greater than capital M. This is say relation 1. Since sequence Sn n is equal to 1 to infinity is non-decreasing sequence of real numbers. Non-decreasing sequence of real numbers. Therefore, by definition of non-decreasing sequence, by definition of non-decreasing sequence, S1 less than or equal to S2, S2 less than or equal to S3, less than or equal to, and so on, Sn less than or equal to Sn plus 1, less than or equal to, and so on, less than or equal to S suffix small n, less than or equal to S suffix small n plus 1, less than or equal to, and so on. S1 is less than S2, S2 is less than S3. Here S1, E and S3, S1 is less than S3. 3 is greater than 1, 3 is greater than 1. Here capital N is smaller than this small n. That is, small n is greater than or equal to capital N. S suffix capital N less equals S suffix small n for all n greater than or equal to capital N. That is S suffix small n greater than or equal to S suffix capital N for all small n greater than or equal to capital N. This is say 2. From 2 and 1. From 2 and 1. From relation 2 and 1. S suffix small n greater than or equal to S suffix capital N, and S suffix capital N is greater than capital M for all small n greater than or equal to capital N. That is Sn, S suffix small n greater than capital M for all small n greater than or equal to capital N. Therefore, by definition of divergent sequence, by definition of divergent sequence, sequence Sn n is equal to 1 to infinity diverges to infinity, or Sn tends to infinity as n tends to infinity. That is, limit n tends to infinity of Sn is equal to infinity. That is, limit n tends to infinity of Sn is equal to infinity. Sequence diverges to infinity. A non-decreasing sequence which is not bounded above diverges to infinity. Hence the proof of theorem second. Hence the proof of theorem second. Theorem 3, theorem number 3. A non-increasing sequence, which is bounded below, is convergent. Non-increasing sequence, a non-increasing sequence which is bounded below is convergent. Proof of this theorem. Suppose sequence Sn n is equal to 1 to infinity is non-increasing and bounded below sequence. Suppose this sequence Sn n is equal to 1 to infinity is non-increasing and it is bounded below. Therefore, by definition, the range set of this sequence is bounded below. Since S is equal to Sn, n is equal to 1 to infinity, is a function from the set I of all positive integers into the set R of all real numbers. Therefore, the range set is bounded below, and this range set is subset of a real number R. Therefore, by definition of bounded below sequence, the range set capital A is equal to S1, S2, S3 and so on, Sn plus 1 and so on, is non-empty subset of capital R, and is also bounded below. Let small m is equal to greatest lower bound GLB of the set S1, S2, S3 and so on. Small m is greatest lower bound of the range set S1, S2, S3 and so on, is equal to GLB for the set capital A. Small m is greatest lower bound of this set S1, S2, S3 and so on, which is a range set capital E. We claim, we have to show that limit n tends to infinity of Sn is equal to small m. Limit n tends to infinity of this sequence Sn is equal to small m. Since m is GLB of the set A, GLB of the set S1, S2, S3 and so on, range set. Since small m is GLB for range set A, or range set A. Therefore, small m is less than or equal to Sn for all n belongs to I. This statement says that S1 is greater than or equal to m, S2 is greater than or equal to m, S3 is greater than or equal to m, S suffix n is greater than or equal to m, S suffix n plus 1 greater than or equal to m, and so on. For any epsilon positive, m minus epsilon is strictly less than small m. This is relation 1, and m minus epsilon less than m, this is relation 2. From 2 and 1 we write, from 2 and 1, m minus epsilon less than small m, and small m is less than or equal to s suffix small n for all n belongs to I, that is m minus epsilon is strictly less than s suffix small n for all n belongs to I. This is say relation 3. M minus epsilon less than S1, M minus epsilon less than S2, M minus epsilon less than S3, and so on. M minus epsilon less than Sn, M minus epsilon less than Sn plus 1, and so on. For every given epsilon positive, for every given epsilon positive, for every given epsilon positive, m plus epsilon is not an lower bound of the set A. M minus epsilon is lower bound. M plus epsilon for any epsilon positive, greater than 0, M plus epsilon is not an lower bond. M plus epsilon is not lower bond for the range set, capital A. Since M is GLB, greatest lower bond, M plus epsilon is not lower bond for the set capital A. Therefore, yes, there exists positive integer n belongs to I, positive integer capital N, such that m plus epsilon is greater than s suffix capital N. Small m plus epsilon is greater than s suffix capital N. Or we write that is s suffix capital N is less than m plus epsilon. This is say relation number 4, fourth relation. Since my hypothesis Sn n is equal to 1 to infinity is non-increasing sequence of real numbers. Since by hypothesis sequence Sn n is equal to 1 to infinity is non-increasing sequence of real numbers. Therefore, by definition of non-increasing sequence, by definition of non-increasing sequence, S1 is greater than or equal to S2, S2 is greater than or equal to S3, and so on, greater than or equal to S suffix capital N, greater than or equal to S suffix capital N plus 1, greater than or equal to, and so on, S suffix small n, greater than or equal to S suffix small n plus 1, and so on. S1 is greater than S2, S2 is greater than S3, S3 is greater than Sn, Sn is greater than Sn plus 1, and S suffix capital N is also greater than S suffix small n. The suffixes are increasing 1, 2, 3 and so on up to capital N plus 1, small n plus 1 and so on. Therefore, we can write S suffix capital N is greater than or equal to S suffix small n for all small n is greater than or equal to capital N. S suffix capital N is greater than or equal to S suffix small n for all small n greater than or equal to capital N. That is S suffix small n less equals S suffix capital N for all small n greater than or equal to capital N. This is say 5. From 5 and 4, we write Sn less than or equal to S suffix capital N, and S suffix capital N is strictly less than small m plus epsilon, and this is true for every small n is greater than or equal to capital N. That is, S suffix small n less than m plus epsilon for all n greater than or equal to capital N. This is say 6. From relation 3 and 6, we write m minus epsilon less than Sn, and Sn is less than small m plus epsilon. This is true for all n is equal to capital N, and relation 3 is true for all n is equal to 1, 2, 3 and so on capital N. Capital N plus 1, capital N plus 2 and so on. Therefore, common result is true for all small n greater than or equal to capital N. Subtracting small m, we obtain minus epsilon less than Sn minus small m less than epsilon for all n greater than or equal to capital N. By properties of modulus, we write modulus of S suffix small n minus m is less than epsilon for all n greater than or equal to capital N. By definition of limit of sequence, limit n tends to infinity of Sn is equal to m. Limit n tends to infinity of S suffix n is equal to m. By definition of convergent sequence, by definition of convergent sequence Sn n is equal to 1 to infinity is convergent to small m, hence the proof of theorem second. Hence the proof of theorem 3. Hence the proof of theorem 3. Now we see theorem number 4. Theorem number 4. A non-increasing sequence which is not bounded below. A non-increasing sequence which is not which is not bounded below, diverges to minus infinity. Diverges to minus infinity. Minus infinity. Proof of this theorem 4. Suppose sequence Sn n is equal to 1 to infinity is non-increasing sequence and is not bounded below. Sn is non-increasing sequence of real number, and Sn is sequence Sn n is equal to 1 to infinity is not bounded below. Therefore, by definition of not bounded below, for any given capital M greater than 0, we must find positive integer n belongs to I, or positive integer capital N, such that Sn is less than minus m for all small n greater than or equal to capital N. Capital N. Since capital M, here capital M is not an lower bound. Here capital M is not or minus capital M. Minus capital M is not lower bound of the set, range set S1, S2, S3, Sn plus 1, Sn plus 2, and so on, small sn plus 1, and so on. Minus m is not lower bound of this range set S1, S2, S3, Sn plus 1, and so on. Therefore, we write for any given capital M positive, there exists n belongs to I such that S suffix capital N is less than minus m. S suffix capital N, therefore, for any given capital M greater than 0, capital M greater than 0, there must exist positive integer n belongs to I such that S suffix capital N is less than minus m. This is a 1. Since the sequence S suffix n is equal to 1 to infinity is non-increasing sequence. Therefore, by definition of non-increasing sequence, by definition of non-increasing sequence, S1 is greater than or equal to S2, S2 is greater than or equal to S3, S3 is greater than or equal to, and so on. S suffix n is greater than or equal to S suffix capital N plus 1, greater than or equal to, and so on. S suffix small n, and so on, greater than or equal to S suffix small n, greater than or equal to S suffix small n plus 1, greater than or equal to, and so on. Here S1 is greater than S2, S2 is greater than S3. Suffix are increasing and value of S suffix is decreasing. Therefore, S suffix capital N is greater than or equal to S suffix capital N plus 1, and so on. S suffix small n is greater than or equal to S suffix small n plus 1. Here capital N is smaller than small n. That is, small n is greater than or equal to capital N. S suffix capital N is greater than or equal to S suffix small n for all small n greater than or equal to capital N. That is S suffix small n less equals S suffix capital N for all n greater than or equal to capital N. This is say 2. From 2 and 1 we write, from 2 and 1 we write S suffix small n. We write S suffix small n less equals S suffix capital N, and S suffix capital N less than minus m for all small n is greater than or equal to capital N. Therefore, Sn is less than minus m for all n greater than or equal to capital N. Therefore, by definition of divergent sequence, sequence Sn n is equal to 1 to infinity diverges to minus infinity, or Sn tends to minus infinity as n tends to infinity, or we may write limit n tends to infinity of Sn is equal to minus infinity. Hence the proof of the theorem. Theorem 4. Hence the proof of theorem 4.